And this is the symbol, the basic symbol for inverter. And inverter is the most basic circuit, okay, having just one input and one output, okay. And this is the truth table, okay. When A is 0, B is 1, okay, and when A is high, output is low, okay. Simple relation between input and output signal values, okay. And this is the voltage transfer characteristic between input and output voltage. So input voltage is taken at along the x-axis, and output voltage is chosen along the y-axis, okay. So it is drawn like this: when the input values changes from 0 to some intermediate values to the highest value of voltage, then how does the output value changes, okay. So let's say when input value is low, 0, the output is inverted, that is high, okay. And when input is still low enough, the output will remain high, okay, for a certain threshold value, okay. And after that threshold value, this is the threshold point, okay. And let's see, after this, when the input voltage crosses this threshold level, goes beyond this VDD by 2 level, okay, then output becomes, then input is read as a high input value, okay. And when input is high, the output will be low, that is output is simply uh, a low or a zero value, okay. So the thing is, uh, there has to be a threshold value, okay. In this case, this is the threshold point, okay, which will decide that which set of values are taken as the low input values, okay. This is the low input value, and this is the range for high input value, okay. So this is the range for low input values, okay, 0 to VDD by 2, and this is the range for high input value, okay, from VDD by 2 to VDD, okay. So if VDD is 5 voltage, let's say VDD is 5 voltage, then VDD by 2 will be 2.5. So input voltage from 0 to 2.5 will be taken as the low input voltage, and the input voltage in the range between 2.5 to 5 voltage will be taken as a high input voltage, okay. For example, so when input is low, the output is high, and when input is high, the output is simply low, okay. And this is the ideal characteristic, this is the ideal transfer characteristic sorry, transfer characteristic means this is a plot between okay. So this is a transfer characteristic, means the curve is plotted between the transfer or the across the port values. For example, this is the this is one of the input parameter, input voltage, okay, and this is one of the output parameter, output voltage. So this is an input parameter, and this one is an output parameter, okay. And that is why this is called as a transfer characteristic, and this is plotted between voltage values. So this is known as voltage transfer characteristic, or in simply short form, it is known as VTC. So VTC of the ideal inverter. No doubt this is the case when the inverter is when the inverter is assumed to be an ideal inverter or ideal circuit, okay. But in reality, practical, you will never see this kind of structure for a practical inverter. Although the practical inverter will behave like this, will be very close to like this, but it will not be exact replica of this, okay. This is the case when the inverter is assumed to be an ideal one, okay. This is the general circuit of an NMOS inverter, a general circuit. Okay, uh, a general circuit, and this uses one NMOS inverter. Okay, so this is the NMOS inverter in the lower side. Okay, and in the upper side, on the top side, we have a load. Okay, now this load can be of made of a variety of elements. Okay, this can be a MOSFET, this can be an NMOS, this can be a PMOS, this can be a resistance. Okay, or such. So this load can be any general load. Okay, so let's assume for the timing that this is simply a load. Okay, we are not defining specifically that what kind of load it is, but this is a circuit element that is connected between VDD, the power supply, and this point. Okay, and this is the NMOS. Okay, and remember that the source of NMOS is connected to ground or the lowest potential. Okay, available. This is the body or the substrate. The body is also connected to the lowest potential available. Okay, by default. And this is the input, this is the gate terminal. Okay, this is the gate terminal. This is the gate terminal. Okay, this is the gate terminal. Okay, this was the source, and this is the drain terminal. Okay, so the load is connected between VDD and the drain terminal of the device of NMOS. Okay, and input signal is provided at the gate of the NMOSFET. Okay, and output terminal is tapped from is taken from a point between the load and the drain of the NMOSFET. Okay. So this is the point from where the output is taken. Okay, and this load in general can be a resistive load, can be a device itself. Okay. Okay, and we will have output capacitance that will be present at the output terminal between the output and the ground. Okay, and this will be taken into consideration when we will perform the dynamic characteristic or switching characteristic. Okay, but for static characteristic, this Cout will be simply neglected, because we know that for steady state conditions the capacitance behave as an open circuit. Okay, so this will just simply become an open circuit, and we assume that no current flows between this point and this point. Okay, so this is the case for a simple inverter, general inverter circuit. Okay, and if it is an inverter, and this output signal, that is V out, okay, which is also equal to VDS, because we know that this is the drain terminal and this is the source terminal, and source terminal is connected to ground. Okay, and this is the drain terminal. Okay, this is the drain terminal. So this V out, or this point, is the potential difference between this drain and the ground or the source. So this is also equal to VDS. Okay, and V out will be inverted value of the input signal, that is V in this case, because this is an inverter. So in this case, V out will be simply complement of V in. Okay, so it means that when V in is low, V out is high, and vice versa. Okay, this we will see. Okay, and also one point to be noted down is that we can apply KCL here, the Kirchhoff's current law. And since we are neglecting this C out capacitance, we are for static characteristic. Okay, so we will not take into account the current flowing through this capacitor. Okay, so the only branch that is visible in this inverter is this branch. Okay, if I apply KCL at this point, at this node, okay, we know that by KCL we know that the input current should be equal to outgoing current. Okay, so we can simply write that IL is equal to ID. Okay, that is IL equals to ID, where ID is the drain current that is flowing through the device between drain and source terminal of the N MOSFET, and IL is the current or load current that is flowing across through the load. Okay, so this is the load current that is flowing through the load, and this is the drain current that is flowing through the MOSFET. And by KCL we can say that this ID is equal to IL. Okay, where IL will be a function of VL, and ID, that is the drain current, will be a function of input voltage V in and the output voltage, that is V out. Okay. Okay. Now coming on to the a more realistic transfer characteristic for the inverter, a more realistic VTC. Okay, voltage transfer characteristic. Look at this graph between input voltage and the output voltage. Okay, if you remember, if you remember, if you remember, uh, what is this? If you remember the ideal curve, ideal VTC characteristic, now you try to compare this realistic VTC with respect to that ideal VTC. Okay, and that was simply flat. If I can draw here for the case of a realistic, that was simply flat like this. Okay, falling at the threshold voltage and coming like this. Okay, but this one, the curvy one, this one is the more realistic curve for a real inverter that is made up of using a device or a NMOS device. Okay, so when you see here, this is the input axis, independent parameter. This is the input voltage. Okay, and this y-axis is the dependent parameter or the output voltage. Okay, and the output voltage is high for this range of values. Okay, output voltage is high. Okay, and for this range of value, the input voltage will be the input voltage is varying between 0, okay, to VIL. Okay, look at here, to VIL, and we call this as the input voltage range that is considered as a low logic value. Okay, so from here to here, the input voltage range will be considered as a logic value, a low value. Okay, from 0 to VIL. Okay, and the output is low. The output is low for this range from here to here. Okay, when input is lying between this VIH and VOH value. Okay, so for this range, the input is considered as a high. Sorry, this is high. Okay, high logic value, HIG H, high logic value. Okay, so what is there here is that there are some new parameters that are introduced. Okay, you will see here. For example, this one VOH and this VOL and this VIL, this VIH and this VTH. Okay, and this the slope. This is the slope that is defined at these points. Okay. So for a more realistic, for a practical inverter, these points are defined because the curve is not following the idealistic curve. It is becoming more sloppy. Okay, it is not falling perfectly at the corners. It is showing a curvy way. Okay, at the edges. Okay, so this is having a certain slope at these points. Okay, so we should introduce these parameters VOH, VOL, VIL, and VIH. Okay. So coming to VOH first, VOH, that is VOH is the maximum output voltage when the output level is logic 1. Okay. So this VOH is the maximum value along the y-axis. We can see easily. Okay. This is the maximum value along y-axis, and y-axis is referring to the output voltage. Okay. So this is the maximum value when output is at a logic 1 or a logic high. Okay. This is the maximum value of voltage that can be attained when the output is at logic 1. Okay. And similarly, we can define it for the low value. This is VOL. Okay. VOL is the minimum output voltage when the output level is logic 0. So this is the minimum voltage when the output is logic 0. Okay. So this O for output and H for high. Okay. And in the substrate we have VOL, O for output, okay, and L for low. Similarly, for input we can define VIL here, I for input, L for low. So this is the maximum input voltage which can be interpreted as logic 1, because we saw that for input side the logic 0 was ranging between this point to this point. Okay, so this was the lowest point when input voltage can be treated as a logic 0, and this was the maximum point when input voltage can be treated as logic 0. Okay, so this is the maximum point, and above this we cannot assume that the input voltage is low. Okay, but below this we will assume that the input voltage is low. So this becomes the maximum point. Okay, which can be interpreted as logic 0 at the input side. So this is how VIL is defined. Okay. And similarly, we have one more parameter, VIH. So I for input, H for high. Okay, and you know that for the inputs at the input side, the value for logic high range is lying between VIH and VOH. Okay, and VOH is the maximum value, and VIH is the minimum value. So beyond VIH or above VIH, we can assume that the input is high, but below VIH, we cannot assume that the input is high. Okay, so in that sense, VIH can be defined as the minimum input voltage. Okay, which can be interpreted as logic 1. Okay, right? So this is how these four parameters are defined in this VTC characteristic. Okay. VOH, VOL, VIL, and VIH. Okay. Now, apart from this, we have some more parameters written over here. This is this VTH. Okay, this is called as a threshold voltage for the inverter. This is different from the threshold voltage for the MOS device. Okay, so be careful that this is the threshold voltage for the device, not for the device. This is threshold voltage for the inverter, for the circuit. Okay, and there was a threshold voltage for the device itself, VT or VT naught, when we were studying the MOS device. Okay, so this is different, and this is generally taken as at the middle point between the lowest value 0 and highest value VDD. Okay, and how to decide this VIL and VIH is that when this curve is plotted between output voltage and input voltage. Okay, then we should decide at what point the slope becomes 1, equal to 1, or because since the slope is going down, so this will be actually -1. Okay, so the point at which this slope becomes -1, that first point will be taken as the VIL. Okay, and again at somewhere here at this point the slope will again become -1. Okay, and this point will be taken as a VIH value. VIH. Okay, so the slope will decide the levels for VIL and VIH. So the condition is that for VIL we should have a slope of -1, and similarly for VIH also we should have a slope of -1. So this is how the values for VIL and VIH is to be decided. Okay. So here, uh, but remember those four parameters, those were important. If you can see, VOL was the lowest point. VOL was the lowest point. Okay, and VOH was the highest value. Okay, so VOH was the highest value, and VOL was the lowest value. And somewhere in between, we were having VIL. Okay, and we were also having VIH. Okay, and we saw that for logic 0 value was lying between VOL and VIL. Okay, and the logic high value, that is H. Okay, the in subscript, uh, H denotes the H is used for denoting high, logic high. Okay, so logic high value was ranging between VOH and VIH here. Okay, so by this there are two terms which are defined, and which is called as noise margin. So we can define a noise margin for low logic. Okay, and we can define noise margin for high logic. So noise margin for low is equal to the difference between VIL and VOL. Okay, that is this particular VIL minus this particular value VOL is the noise margin for low logic. And similarly, the noise margin for high logic is equal to the difference between VOH and VIH. VIH. Okay, that is VOH minus VIH. Okay. So, and this is a very important parameter in digital circuits, especially in digital circuits. Okay, we define that in a digital circuit, the noise margin is the amount by which the signal exceeds the threshold So look at here. This is a range. Okay, this is a range for logic 0 value. It can be a 0.5 voltage. It can be a 0.6 voltage. It can be a 0.65 voltage. It can be 0.7 voltage. It can be a 0.79 voltage. Okay, so all of these actually a band, it is a range. Okay, so there is a tolerance, and that tolerance is actually VIL minus VOL, and that tolerance value or that range value is actually taken as the noise margin. Okay, and so by definition we can say that if we say that VOL is the lowest value, okay, then if the signal exceeds this VOL by V by an amount equal to VIL minus VOL, okay, then still we will say that the signal value is in logic 0. Okay, although the signal is exceeding this VOL by a certain amount, but still it will be taken as it will be treated as a logic 0 value. Okay, so this is not a single value, this is actually a range. So keep this point in mind. So for example, a digital circuit might be designed to swing between zero point 0.0 and 1.2 voltage. Okay, so we can design a digital circuit that will swing between 0 and 1.2 voltage. So in that case, this VOL will be 0 voltage, and the VOH is 1.2 voltage. Okay, with anything below 0.2 voltage considered as 0, anything below 0.2 is considered as 0. So in this case 0.2 voltage, okay, uh, is the value for VIL. Okay, and in this range between 0 and 0.2, any value that comes, be it 0.19, be it 0.05, be it 0.1, or be it 0.07, whatever value is lying between this range will be treated as a logic 0 value. Okay, and anything above 1 voltage considered a 1, considered a 1. So anything above 1 voltage will be taken as a logic 1 value. Okay, so in this case, for example, for this specification, okay, if for this statement, if I say that what is the value for low noise margin and high noise margin, okay, so first you should be able to mark the values for VOL, VIL, VIH, and VOH. Okay, and after finding these values, the noise margin for low, that is equal to VIL minus VOL, that is 0.2 minus 0. This simply becomes 0.2, the noise margin low, and the high noise margin is equal to VOH minus VIH, that is 1.2 minus 1, that is equal to 0.2. So in this case, high noise margin is equal to low noise margin. Okay, but it may not be the case in every other situation. Okay, this is just one example. Okay, this is clear how to define the low noise margin and high noise margin, right? But look at here that there is a region, that is there is a gap between VIL and VIH. Okay, so look at this gap, look at this gap. For this gap we have not defined anything, that if suppose if a value that lies between 0.2 and 1 voltage, let's say 0.8 voltage, okay, then what logic will be decided for this 0.8 voltage? Okay, but it, because it is not defined here, so it will remain undecided. The circuit will may not be able to decide, the output may not be properly read at what it is actually. It is is it a logic 0 or is it a logic 1? Okay, it may actually remain undefined, or randomly it may be plugged into logic 0, or it may get locked at logic 1. It can occur at you know at a random fashion, at a random in a random fashion. Okay, so this is still undecided. There is a still undefined region between VIH and VIL. Okay, and this region is also important. This gap is also important. Okay, so that we can uh, increase or decrease the value of noise margin values, noise margin band. Okay, and there is a significance for each of these three bands. Okay, so there will be circuits with having low noise margins, very noise margins. There would be circuits having broader noise margins. Okay, so the circuits having broader noise margins will be having narrow undefined region, and the circuits having narrow noise margins would be having broader undefined regions. Okay, so this will depend on the application at means what kind of application you are trying to build the circuit for. Okay, but these fundamental things should be clear in the starting. So the power and area consideration. The DC power dissipation, the product of its power supply voltage. We know that power is simply defined by the product of voltage and current passing through a device. Okay, so the product of its power supply voltage and the amount of current down from the power supply during steady state or in state or standby mode. Okay. So PDC, that is power in DC mode or in steady state mode, is simply equal to VDD dot IDC. VDD is the supply voltage and IDC is the current that is flowing through the device. Okay, that is flowing through the circuit. Okay, and being more specific, because we know that the noise margins for low and high could be different. Okay, so in those cases it will become by taking the average of the two noise margins. Okay, it will be VDD by 2 into IDC when Vin is low plus IDC when Vin is high. Okay, okay, and one very important point is that since the device size are shrinking, they are becoming smaller and smaller. So in deep submicron technologies, okay, the sub-threshold current, that is the current that flows through the device when the device is in cutoff. Because we know that even when the device is in cutoff, the current that is flowing through the device is not completely zero. There is still a very small amount of current flowing through the device when it is in cutoff. Okay, and that cutoff current can be neglected for a larger device. But when the device becomes smaller and smaller and smaller, then that even that threshold current, sub-threshold current becomes an important parameter. Okay, and that will lead to more power consumption. Okay, so it is to be taken into account when the device is becoming is shrinking down, is being scaled down, is being made uh, smaller and smaller and smaller. Okay, the area, we know that the area is being reduced for the newer technologies. Okay, so there has to be certain parameter, certain reference parameter, which can be taken all the times to to refer to the calculations. Okay, and generally it is taken as the area of the gate, area of the gate. Okay, and area of the gate looking from the top side. So we know that it is having gate, beneath gate we are having a channel. Okay, and the channel is of length L and it is of width W. So the area becomes W into L. Okay, and this is taken as a reference parameter in terms of area to compare any two devices, any two circuits. Okay, so now that was the case when we were taking a general load. Okay, a general inverter was there. Now let us become more specific and see the different types of inverter that are there, that are being used actually in the practical world. So the most simplest among them is a resistive load inverter. The name implies that it will having a load. It is having a load that is a resistance. It is having a resistive load. Okay. So look at here. This is one NMOS. Okay, and this is a load that is made up of a simple resistance. So a resistance is connected to act as a load in this case for this particular inverter, and it is now called as a resistive load inverter. Okay. So generally we will call this as a load device, and we will call this as a driver. This is a driver, and this is the load. Okay. And this is also called as the pull up network, the pull up network, and this one is called as pull down network. And we will see why it is called like this. Okay. But for the timing, you just keep this in mind. This is the lower is called as the pull down network, the upper one is called as the pull up network. Okay. Now again, this is similar, that there is a power supply VDD, there is a ground supply, this is the source. Okay, this is the source, this is the drain, and this is the gate of the device. Okay, and this is the point that is between the drain and one of the terminal of the load. Okay, and from this common point the output is taken. We call this as V out, and this is also equal to VDS, because this is the same voltage that is appearing across the drain and the source terminal. Okay, so in this case VDS becomes equal to V out. Okay, and this is the supply voltage, and input voltage is applied at the gate of the device, at the gate terminal of the NMOS device. Okay, this is input voltage V in, and in this case this is also equal to VGS. VGS means the voltage between gate and source, gate and source, because since this source is connected to ground. Okay, the source is connected to ground, so it simply becomes VGS is equal to VG minus Vs, that is equal to VG minus 0 or VG. Okay, so this, since this source is connected to ground, so it becomes easier to write in this fashion, that V in is equal to VGS and V out is equal to VDS. Okay, and remember the KCL, we will apply KCL at this point. At this point we will apply KCL to analyze the circuit. Okay, and at this point IR, this IR is equal to ID, where IR is the load current or the current flowing through the resistor, and where ID is the drain current flowing through this device. Okay, so we know that the device can be in three modes of operation. It can be in cutoff, or in saturation, or in linear. For when the device is in cutoff, it means that, or when the input voltage is smaller than its threshold device is its threshold voltage. Okay, when the input voltage is smaller than its threshold voltage, then the device would be in cutoff. Okay, someone is waiting outside. Okay. Okay, so when input voltage is smaller than the threshold voltage of the device is cut off. Okay, this becomes cut off, or this simply behaves as an open circuit. This does not conduct. This does not conduct, right? So when it is open circuit, this is not conducting. In that case, this point, this terminal will not be in contact with this terminal. Okay. No current is flowing through this. The current flow through this branch is 0, and in that case the output terminal will be connected to, the output terminal voltage will be equal to this particular voltage, that is supply voltage. Okay, so this thing is can be written like this, that output voltage is equal to supply voltage, when the device is cut off, or when this is not working. Okay, when this is not working, we can see that this particular terminal is connected to the supply voltage directly, and since this branch is not working, so there is no path for a current to flow, and in that case IR would be equal to ID equal to 0. Okay, and simply the output voltage will be equal to the supply voltage, that is VDD, when the device is cut off, right? Okay. Okay. Now when we increase the input voltage, beyond threshold voltage, the device starts to conduct. Okay, and it may be either in saturation or in linear mode of operation. Okay, the NMOS device, the device goes into saturation mode. Now this is important here, that to decide that when we have increased zero input voltage from 0 to some voltage higher than the threshold voltage. Okay, in that case, in what mode our device is operating in. So this is important to decide. And if you remember the equations for NMOS, there were for saturation we were having the condition that the VDS should be greater than VD set, right? You remember, VDS should be greater than VD sat, and this what was actually VD sat? VD sat was actually nothing but VGS VGS minus VT, the threshold voltage. Okay, the threshold voltage, VT naught. Okay, so when VDS becomes greater than this VGS minus VT naught, we say that the device is in saturation. And for this case, this is actually satisfying. Okay, for this case, this is actually satisfying. How? Let us see. Let us see. Okay. VDS is what? VDS is this output voltage V out. Okay. And VGS is what? VGS is equal to the input voltage V in. V in. Okay. Now we had started from VGS input from 0. Okay. Let's say this is the scale. This is the scale. Okay. Let's say this is the maximum point. Let's say this is V D D. Okay, and let's say this is the threshold voltage of the device. Threshold voltage of the device somewhere here. I am taking a general typical values. VDD may be 5 voltage. Okay, and let's say we are starting from 0 voltage, and VT naught may be 1 voltage for the device. Okay, 1 voltage for the device. Now, for this case, for the first condition when the device was in cutoff, we had assumed that the input voltage is below VT naught. That is, it is lying in this region. It was lying in this region. Now we have increased the input voltage beyond VT naught. So this input voltage has now risen to, let's say, this particular point. It has gone just above the value of VT naught at this point. Okay, at this point. Now, under this situation, okay, what is the value of VDS and what is the value of VGS minus VT naught? Okay, VGS is equal to input voltage. Okay, so this is the input voltage, input range, and VGS minus VT becomes this one. This range becomes VGS minus VT, VGS minus VT. VGS minus VT is actually this range, which is small, which is small, okay, which is small, and VDS is the voltage that appears across this device, and device starts to conduct. We don't know that in which mode the device is in. It is in linear or saturation. We have to decide. But the thing is that since the input voltage is higher than its threshold voltage, it is conducting, and a significant amount of current is flowing through this device. Okay, and when a current is flowing through this device, okay, the output voltage will rise. The output voltage will rise, and we can very safely assume that the particular output voltage, the VDS, would be greater than this particular range. And what was this? Actually, VGS minus VT naught. Okay, we have not increased input voltage above threshold voltage by a big amount. It is still in the vicinity of this VT naught, so that this particular range is very small. This particular range is very small. Okay, and the device will be in saturation, and this condition will be followed. Okay, so when you go just above VT naught at the input side, the device will enter into saturation. Okay, satisfying this condition. Okay, and apply KCL at this particular branch. Apply KCL that says that IR is equal to ID. Okay, IR is the current through the resistance, and this is the value of the current flowing through the device. And since the device is in saturation, okay, so it has to be uh, id sat id saturation. Okay, and we know the equation for saturation current, that is like this: kn by 2 v in minus vt naught whole square. Okay, okay. So we had seen this condition. Now uh, with increasing input voltage, when the input voltage becomes more and more, okay, the drain current of the driver also increases. The drain current through the device, that is also called as a driver, will also increase. The drain current will increase through the driver, and the output voltage V out will start to drop, right? And eventually, for input voltages larger than V out plus Vt naught, the driver transistor will enter into linear region of operation. Okay, so it means that when we increase the value of input voltage, when we keep on increasing the value of input voltage, the device will enter from saturation to linear mode of operation. Okay, and at larger input voltages, the transistor remains in linear mode as the output voltage continues to decrease. Okay, so in that case, when you apply KCL, okay, when you apply KCL, that is IR, the current through resistance, equal to the current through the device, that is ID. Now in this case, when the device is in linear mode of operation, we should use the linear current, not the saturation current. Okay, and this is the equation for linear current. This is the equation for linear current. Okay, 2 into V in minus Vt naught into V out minus V out whole square. Okay, and this I leave this this task up to you to decide to verify this thing, that when we increase the input voltage to a certain high value, then how does the device enters into linear from saturation. Okay, earlier it was in saturation, that is verified, but now it is entering into linear mode of operation when we increase the input voltage above, when we make input voltage higher and higher. Okay, so try to verify this, try to satisfy this condition, that if you are able to understand this thing, you tell it's okay, otherwise you tell me. I will explain this in the next class. Okay. Now, when the device is in linear mode and when we apply KCL, so IR will be equal to the ID linear, and this is the equation for drain current when the device is in linear mode of operation. Okay. And these are the three conditions that we had just seen. When the input voltage was smaller than the threshold voltage of the device, the operating mode was cut off. Okay. And when input voltage was satisfying this condition, that it was greater than threshold voltage but smaller than this amount, it was in saturation. Or when input voltage was higher than this particular term, this is the same term that is appearing here. Okay, so it enters into linear. Okay, so one more thing, that how it is acting as an inverter. How it is acting as an inverter, let us see. So when input is zero, when input is zero, let us say zero, the device will be in cutoff and it will not operate, it will not conduct. So this terminal will become, this branch will become open circuited. Okay, and in that case output terminal is connected to VDD directly, and this VDD will be equal to 1 or high voltage. So when input is 0, output is 1. This condition is satisfied. When input is low, output is high. One condition is satisfied, right? Now, when input is high, when input is high, okay, when input is high, let's say when input is 1, the device operates, the device starts to conduct. Okay, it will conduct either in saturation or linear, we know that. But whatever, if it, whether it is in conducting in saturation or linear, it doesn't matter. The thing is that a drain current is flowing through the device, it is conducting. Okay, it is just a matter of resistance value, that you know that the when it is in linear mode there is a different resistance shown by the device, and when it is in saturation mode the resistance value changes. That thing is there, but we know that the device is conducting, it is passing a significant amount of current through this. Okay, and we say that the device is on. So when input voltage is 1, the device is on, this is conducting, and we can assume that this is acting as a short circuit. Okay, and this is exhibiting a low value of resistance. We can just for the timing we can say that. And in that case what will happen, that this particular branch is effectively connected to this ground. And we can say that this out is connected to ground or zero. This is the case here. So when input is high, output is low. So it is acting as an inverter. It is acting as an inverter, right? So when input is high, output is low, and vice versa. So this acts as an inverter, and we had seen three conditions: the cutoff, saturation, and the linear. And these are the three conditions stated in this, tabulated in this table format. Try to understand this. Okay, then we will analyze it further in the next class. So we will try to formulate, we will try to figure out the four parameters that we had defined for finding out the noise margin. And what were those parameters? That were VOH, VOL, VIH, and VIL. Okay, we will see how to calculate these parameters in the next class.